So welcome. So today we're going to have a quick look at oscillations and waves. And this is chapter 19 out of our textbook. And this is an area which can lead to some confusion because it is oscillation and waves. And people tend to blur the two of them together. And it's a really good idea to try and figure out what's the oscillation and what's the wave. And then it kind of gets sorted out. So first of all, examples of oscillations. A good example of an oscillation is a pendulum. Things tend to swing backwards and forwards with a steady rhythm. Another example that's classic is the mass on a spring. Mass on a spring oscillates backwards and forwards with a steady rhythm. If you play with an oscillator, then you learn a few things. You learn that some things affect the frequency of oscillation and some things don't. So for example, with a pendulum, the mass of the pendulum does not affect the frequency of oscillation. Big, massive mass, little mass, all the same. I'm talking about a pure pendulum, where, having said the mass doesn't affect it, the mass has to be bigger than the string. There are other pendulums like a solid pendulum where we have the significant mass in the string. I'm imagining a little ball of material on the end of a string. The actual amount of material in that ball doesn't matter. More matter in that ball gives you more energy storage. If you think about it, whether you slide it up, whether you push it to the side, or whether you lift it and carry it to the side, you've put potential energy into it. And the more mass it has, the more potential energy you've put in. If I put more energy in to start with, I'm going to swing for longer until all that potential energy is lost through friction as heat. So massive pendulums tend to run longer before they wind down than light pendulums. But they don't go any faster. They don't oscillate any faster. And also the other thing that is a bit shocking is that the amplitude, how far you move that mass away from its equilibrium position, doesn't matter. Now if I go so I'm at 90 degrees, it affects things. But if I go 15 degrees backwards and forwards, it makes no difference. And most people think that if you move further away, it must slow the pendulum down. But as you move further away, it goes faster through the middle, so the time stays the same. The first person to notice this and comment on it, that in the European tradition we talk about, is Galileo. Galileo was in northern Italy. Most of the churches or the communal buildings had high ceilings, and they'd light them by hanging chandeliers with candles. And every day somebody had to light the candles, and every day somebody had to unlight the candles. And there's two ways you can deal with it. And a modern church like that, they would have a kind of machine that would just lower the thing to the floor. Then you'd change the light bulbs. Then you'd wind the thing back up. But back in the day, I'm pretty certain they had a guy on a ladder who would go up and light the candles. And one day, they lit the candles, and then as they're walking away, they turn and they hit the chandelier with the ladder. And it starts swinging. And Galileo had an interest in timing devices. He was doing work with motion, and he was interested in keeping accurate marks on time. And so he would use droppers. He would have liquid in a tube which formed little droplets of water. And as long as the level doesn't change much, the little droplet, I guess, stays about the same. Maybe, actually, I don't know much about it. Maybe it doesn't matter whether the level changes that much. I'm not sure. I should imagine that the level changes matters a little bit. But he had droppers, and he would time things. Or how long it takes to fill a bucket could be another way. They'd use candles, how long it takes to burn down a candle. That could be another measure. Pulse, as long as you're calm, is another measure of time. And so he watched this thing swinging, and he's realizing, oh my word, that's nice and regular. And he measures his pulse and he times it, and when the thing's swinging a lot, he gets a certain frequency, and when the thing's swinging a little bit, he has the same frequency. And so he goes, that's a timer. I can use that. And he started playing with timers like that. So very interesting. One of the points that's not so, that when you think about it, he's observing something that he's going to write down in his notebook, which will be talked about by people 400 years later. This is 400 years ago. And so it's significant. But he didn't get excited. He didn't, his pulse didn't race. Like, oh my word. I had this one time in my life when I did this like killer experiment that was like important. It took me a year to make this sample. And I'd given up on getting the sample. I'd done other experiments to get my degree. And then at the last minute, this sample showed up. And I put it in the machine, and I was going to test it. And I turned the machine on, and part of me didn't believe it was going to work. And it started to work. And I shouldn't tell you this, really. I honestly went a little faint. It was like, it's working! And then it stopped working. So it worked for like a split second. But I felt so excited. My blood pressure must have been quite high. And, or low, I found one or the other. But something was happening, and I was like... So I'd have told you that the pendulum would have changed its frequency because my pulse would have been racing. But so for him, he wasn't like that. He was very cool. Okay. And then from then, people learned other mechanisms of vibrations. There's vibrations whether we like it or not. As a Boy Scout, you learn to break step when you cross a wooden bridge. Because if you all match in step, which Boy Scouts tend to do, it's kind of like you keep up, you get into this rhythm, and you go into the river and you're all bouncing at the same rate. You can cause damage. If you go to Busch Gardens and you go to the, it used to be Dragonland for the little kids, now I think it's Elmo Land or something. They have these rope walkways, they're like netted, and they go between one building and another. And inevitably there's some middle school kid bouncing in the middle and getting the whole thing to really oscillate, because he found the natural frequency of that object. So natural frequencies, so oscillations occur, and things have natural frequencies of oscillation. If I bang the table, it sounds different than if I bang the computer desk. And you can hear the difference in the sound because you hear the difference in the oscillations. So we've got to deal with these things either because we want to do something with them, or we've got to even try and avoid them, but we've got to deal with them. So what we say is vibrations, and I said of a pendulum, but I'm also broadened it actually to include mass on a spring, because that's probably what you're going to face, because it's simpler mathematically than we don't see it here, but it is simpler mathematically than a pendulum. So we say a simple pendulum consists of a mass suspended by a very light rod or string. The mass swings backwards and forwards. The period, there's a new term, period, that is the duration, the time for one complete swing of the pendulum swing is constant. So a pendulum with a certain length will have a certain oscillation. You can change the mass and it won't make a difference. So it's useful. We say the period of a pendulum swing depends upon the pendulum's length and the strength of gravity at the field at that point, how strong the pull of gravity is. It does not depend upon the pendulum's mass or the amplitude of the pendulum swing. So two things it does depend on and two things it doesn't depend on. So if you do the math, you find that the period t, this is period, is equal to some constant 2 pi times the square root of the length of the pendulum over the gravitational constant, which is, this is 10 newtons per kilogram. And this is measured in meters. And it works. By the by, geologists, or petrologists really, geologists who are employed by gas and petrol companies sometimes use very sophisticated pendulum machines to try to detect changes in the Earth's gravitational field, little g, at different points. Because the idea is if there's terrain that contains a gas field or an oil field, the density of the material under the detector will be different than somewhere else. And if they can detect that the difference in density, then they can learn something about the subterranean structure. We can do the same thing with just a spring with a mass attached. And as we move it, it will oscillate backwards and forwards. So this guy's going to oscillate that way, and this guy's going to oscillate that way. And can you see this guy's part of a circle, so it's a little bit complicated, but this thing's a nice straight line, so it's more straightforward. And we say the period of a mass on a spring depends upon the system's mass, system meaning the mass is mass. And the spring constant, spring constant is a number which tells you the force per meter displacement. So a stiff spring has a big K, and a soft spring has a little k. It's like a figure of merit for the stiffness of a spring. The period does not depend upon the spring's length, and it does not depend upon the mass, the amplitude of the mass's spring. We get a very similar equation. T is equal to 2 pi root m, which is in kilograms, and K, which is newtons per kilogram. Okay. So just two by the bys. You don't need to remember those equations. It's like, this is where it starts getting a little bit complicated, confusing. If I want to study oscillators, I will plot the position of the pendulum bob or the position of the mass in time. So I do a graph. And I get a graph which looks like this. And for small oscillations, I get a sine curve. Now, you may have done trig or not, but sine curve is a trigonometric function. It's like, you can look it up in the table, or your calculator has sine functions in it. But it's kind of like, it's the shape of the electricity that comes out of the socket. Sine curves are everywhere. And we need to be able to talk about different features of this curve. And the important things are the amplitude and the period. They're the two most important things. The amplitude tells you how far you move away from the equilibrium position, and the period tells you how quickly or slowly this change occurs. We say if the pendulum swing is small, less than about 15 degrees either way, its motion is special, and we call it simple harmonic motion, SHM. And the same thing goes for a mass on a spring, and SHM is very, 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 very important. When you get SHM, you get a sine curve. We can identify the amplitude of the period of the oscillation. The amplitude is the maximum displacement of the pendulum bob, if we're talking about pendulums. So it's that distance from the extreme to the middle. Now, in my wife's department, which is Communications, Sciences and Disorders, in their department they often talk about the amplitude as being from the positive peak to the negative peak. And that's called peak-to-peak amplitude. And it's preferred in some instances because it's easy to measure. But physics traditionally has called the amplitude from the middle to the outside edge. So there's a little bit of potential for confusion there, because what happens is, although people should say peak-to-peak amplitude, they end up saying amplitude because they never use anything else. And we say amplitude because we never use peak to peak. So 2 words for the same thing. Then the period is the time for the repeating. Now, you can say from the positive maximum to the positive maximum, or you could say from the negative to the negative extreme, or you could say from the middle, but you've got to say the middle going upwards to the middle going upwards. And the most common mistake is people will say that's the period because it's from the middle to the middle, and that's not the repeat. It's from the middle going upwards to the middle going upwards, or the middle going downwards to the middle going downwards. Your amplitude is measured in meters, your period is measured in seconds. Slow oscillations give you long amplitudes. Quick oscillations give you short amplitudes. People tend not to like to talk about things that get very much less than 1. It's just feel less comfortable with it. And somebody at some point said, let's do some math. And they invented this term frequency. And frequency is the number of swings or cycles that are completed in 1 second. So you can have a 53.5 hertz cycles per second, or 17.2 cycles per second. You went through 17 complete cycles and then 1/5 of another cycle. The unit for frequency is hertz. It used to be, when I was a student, it was cycles per second, and they stopped, well, they didn't stop using it, they named it after Hertz, who was a famous scientist who worked in this kind of area. In naming it after him, they made life more difficult for a lot of students, because when it said cycles per second, you knew to take the number of cycles and divide it by the number of seconds. Whereas when it's called the hertz, you don't necessarily know that. You're not told by the unit what to do. And so it makes things a little bit harder. One of my friends, I don't know if this is true, or maybe you guys can help me. So as a kid growing up in England, we would have spelling tests all the time, because the spelling of words in British is not rational. Sometimes it's OW, sometimes it's OGH, sometimes it's ANCE, sometimes it's ENCE. It gets really confusing. And I just assumed that they had spelling tests all over the world. And then one of my friends, you said it's interesting, I don't know which country they were from. I think they were Spanish speaker. They said, we never had spelling tests. It's like you spell it the way it sounds. Is that true? Sort of really no spelling tests. So I'm very envious if there was no spelling test, because I can't spell. And but I'd love a language where you didn't have to worry so much about it. But it's just when you get a language that's a mixture of so many different influences, it tends to be confusing. When I was doing teacher training, I asked my teacher trainer about ways to improve my spelling, and they said, well, practice or read more. I said, but aren't there like rules for this thing? And they gave me the rules, and I think they gave me 37 rules for spelling. And it would say things like, if it is an Anglo-Saxon root and it follows something, then you spell the sound this way. And if it is a Germanic root or Scandinavian root, then you spell it this other way. It's like, how do I know? And they said, well, you got to remember that. So it was a bit annoying. So the frequency is hertz. It's 1 cycle per second. And so we can see that frequency is equal to the 1 over the period. That's kind of nice. It's 1 over the period. So if the period is 5 seconds, the frequency is 1 over 5 hertz. If the frequency is 2 seconds, it's 1 over 2 hertz. It's very nice. So we had 2 natural units, amplitude and period, and then we made another unit up so we can talk about it as we wish. When we connect together a whole bunch of oscillators, so here's like a whole bunch of pendulums that are connected together by bits of elastic. Then when I'm going to show it from above. When this one oscillates, it kind of pulls on that one, pulls on that one. So you get this like delay. And that forms what looks like a wave. It's beautiful. A wave is caused by a sequence of connected oscillators. For the most part. Sound is a little bit, they're not so easily, you can't imagine them so easily connected, but the particles do bounce into one another. But certainly a spring, for sure, is a sequence of connected oscillators. And when we plot this out, well, you're going to plot, let's take a picture of the wave, and we're going to look at its x position and its y position, vertical and horizontal, if you like. So this is a picture at a certain time for many oscillators, whereas the previous one was a graph of position versus time for one oscillator. So they're not the same, but they look identical. You know, they're both sine waves. One of them has different axes to the other, but we tend as people to forget axes. And so we've got to be careful about that. Yeah, the amplitude is from the middle to the extreme again, same value. But this repeat is now a repeat distance, not a repeat time. And we call that the wavelength. So we say we can identify the amplitude of and the wavelength of this wave. The amplitude is the maximum displacement of the pendulum's bob, and the wavelength is the distance of one complete wave. Somebody, so for instance, we can imagine shorter and shorter waves. Eventually they get less than 1 meter long, so we're talking about 0.8 meters for our wavelength, 0.6 meters for our wavelength, 1,000th of a meter for our wavelength. And people said, I don't like talking about these numbers that are less than 1, so what can we do? And they invented this thing called the wave number. And the wave number is in 1/meters, and it is, wave number is equal to 1/wavelength. So we had frequency equals 1/period. So now we have wave number equals 1/wavelength. So same relationship. Unfortunately, this wave number was given a very weird symbol. It's a very weird symbol, but that's what it is. And it is measured in 1/meters. Can you see how easy it is to get those two confused? Let's play a little more ball with a wave. So imagine you have a whole series of oscillators. Could be water droplets on the surface of a pond. Could be masses with springs on. Whole series of oscillators. They're connected together by surface tension or by little pieces of elastic or whatever. And you can look at that and you can measure how long it is between crests. And that will give you the period. And you can measure how far it is between crests. And that will give you the wavelength. The period is like how long it takes you to make a step. And the wavelength is how long that step is. The crests seem to come towards you. And you'd like to know how fast they move towards you. So you get the velocity. And if you were a person walking towards me, I would say, well, how big is your step length? That's like the wavelength. And how many steps do you take per second? And that's like the frequency. So that's in principle where that equation comes from. V equals F lambda, or lambda F I wrote in this case. And if I say, I don't like working in frequency, then you can say, lambda times 1 over period. That's also my thing, which equals lambda over t. So they're all different ways of saying the same thing. This is a really important equation. So some practice examples. If we have a frequency of 4 hertz and a wavelength of 4 meters, what is its speed? V equals F lambda. 4 hertz and 6 meters is 24 meters per second. 24 meters per second. Yep. And if the frequency is 10 hertz and the speed is that, what is the wavelength? Lambda is equal to V over F, which equals V, which is 5 over F, which is 10, which equals 0.5 meters. Just using that expression. And V equals F lambda. In this case, I want to find its frequency. F is equal to V over lambda, which equals 8 meters per second over lambda 2 meters, which equals 4 meters per second. I'm sorry, no, that's not right. I'm trying to find frequency, 4 hertz. Yep. So, okay. So we like waves. Waves are interesting. What is, when you stand in the ocean, you're not in the breakers, you're further out. You're beyond where the white foam is. You stood further out. And the things are coming towards you. What do you feel? Are you particularly pushed back towards the shore? Or are you pushed up and down? When you're a fair distance out, not in the foam, you're further out. So it's up to your chest, maybe you're bouncing up and down, and these crests are coming, nice and gentle. Do you feel that way, or mainly up and down? It's mainly up and down. Near the shore, the waves tumble inland, but not further out. What pays for all that energy near the shore? It's energy, clearly, isn't it? It's coming to you via these nice steady waves. So waves transport energy. As I'm talking to you, there's no molecules from my mouth are entering your ears. That would be kind of disgusting. You would be sick all the time. But my energy from my mouth is entering your ears. So this molecule vibrates that molecule, vibrates that molecule. So it's the energy that we send to people. It's not the stuff. And when we look at this, we find that there's waves all over the place, but we can break them down into 2 types. We have the so-called transverse type, and we have the longitudinal type. And the transverse type is the thing where the motion of the material is at 90 degrees to the wave. The wave's going in that direction, but the energy is going in that direction. This crest is going like that. Can I show you it? Yeah, can I show you that? Can you see the crest is moving backwards and forwards? So the crest is going like that. The energy is going like that. That's a transverse wave. And the other one is longitudinal wave. Unfortunately, I can't show you it so well, but if I squash these guys into each other, then that's a longitudinal wave. So speaking, sound, is a longitudinal wave. The air molecules hit the air molecules hit the air molecules. That's longitudinal. Whereas if I take a rope, that's a transverse wave. So we say if the motion of the medium's particles are perpendicular to the direction of the wave propagation, it's transverse. Transverse waves cannot propagate or travel through liquids. That's a bit interesting. There's got to be some elasticity. There's got to be something. Or gases, for the sake of it. Actually, even more so with gases. Because the particles are not holding on to each other. They're just next to each other. Longitudinal waves, they're the ones where you bump into each other. The motion of the medium's particles is parallel to the direction of the wave propagation. The wave is longitudinal. Oh, I'm so sorry about this. It's cut and paste. Longitudinal. Longitudinal waves can propagate through gases as well. So liquids and gases. Why do I care about that? There's a very strange thing happens. Here's the globe. And here's a site of an earthquake. And we can tell where the earthquake is because we have seismic stations. And what they do is, as the energy spreads out, it comes in two forms. There's a longitudinal type of wave, and there's a transverse type of wave. And the longitudinal wave arrives first because it travels faster, and that is called the primary. And the transverse arrives second because it's slower, and that's called a secondary. And you can remember because the S is in transverse. There's no P in transverse. And there's no P in longitudinal, but there's no S either. Yes?
What about energy C?
Sorry?
What about energy C?
Okay, so...
Electric C.
Oh, so electricity is something again. That is, in terms of your electrons, they are pushing and pulling each other. Well, pushing each other. So I could argue that it is a longitudinal wave, but we tend to draw it as a transverse. Okay, I'll get to that in a minute, actually, because it gets confusing. So the primary arrives first and the secondary arrives second. So all these stations, they say, what's the time difference between the primary and the secondary? What's the time difference between primary and secondary? And it causes, if I know there's that time difference for the primary, and I know there's a different time distance from the secondary, I know that, the point where the energy came from is so far away. I can figure it out. So that's how I get all these substations telling me it's there, it's there, it's there. What they can tell me is how far it is away from them. So there's all these circles crossing, and they're all pointing to one place. The interesting thing is if you go to the other side of the world, all those substations, all those sensing stations, they only receive the primary. They get no secondary. There's no transverse waves. And so the question is why? And the best answer is that inside the Earth there's a liquid core. Now inside the liquid core there's a solid core, so it's complicated. But there's this three-dimensional sphere of liquid. And so the energy can't go through that liquid as a transverse wave. And so that's good evidence for the fact that there's a liquid core to our Earth. You can't say that, you can't look at the magma that comes out of a volcano and say, look, it's liquid, because that's just hot, molten rock, which actually gets molten quite near the surface. Doesn't tell you about the deeper layers. So that's interesting. If we have a system whereby waves, different waves, can occupy the same space, they interfere with each other. So if I hum and a companion hums, you hear the combination. Most of the time, sounds are complicated. Most of the time, light's complicated. Most of the time, mechanical waves are complicated. But if you're careful with your experiment, you can make the sound only one tone, one frequency. And then observation becomes boring but simpler. Or you can make the light one frequency. Then observation becomes boring but simpler. And what you find is, if I have a speaker in that corner and a speaker in that corner, and I'm making, if I have a speaker here and a speaker there, and I'm sending sound waves out, then if I stand here, the way I've drawn it, a compression from one speaker arrives with a compression from the other speaker. And they add together. So I get a really big compression, a lot of pressure. And then when it's in the rarefaction time, the low pressure time, it's a low pressure with a low pressure. So I get a really low pressure. So if I plot a graph, and here's my high pressure for the compression from one wave, and here's my high pressure from the other wave, and they overlap in space, I add them together. So that's a really high pressure. And here I add a low pressure with a low pressure, which is a really low pressure. And so the effect is magnified, or at least it's doubled, it's added. So I would hear louder sound. But if I go to a place like this, I'm going to draw this a bit more carefully. So I go to a place like that, where I'm getting the compression from one speaker, but I'm between compressions in the other speaker. Then I have a high pressure from one side, and I have a low pressure from the other speaker. And the high and the low cancel. And so I get no sound. Now, this happens. You don't notice it with a stereo system because there's complicated sounds coming out from each. But if you could wire up your stereo system so that you had what we call a pure tone, 100 hertz, 1,000 hertz, just hum, and I could do it in phase from both. I could stand at one place and hear loudness and go to the side and hear quiet. And loudness and quiet and loudness and quiet. It's the most amazing thing. And what's even more amazing, if I could get laser light from the two speakers, from the two light sources, I could see brightness and darkness and brightness and darkness. That's very much a wave effect. Anything that behaves in waves will interfere. I can actually get interference when I don't even intend to get interference. If I hum towards the wall, then my wave bounces back. Now, let me ask you a question. If you go to a swimming pool and you splash a wave towards the wall, so a crest goes towards the wall, and you watch the thing bounce off, what comes back to you? If a big wave comes towards you, goes away from you and hits the wall, what comes back to you? Is it a wave or is it a trough? Is it a crest or is it a trough that comes back? What do you think?
Sometimes different.
It's sometimes different, but for water it's always going to be the same thing. A wave goes to the wall, and a wave comes back. Let me go a bit off script for a minute. I'll keep that. But let's do this. I want to go here. I want to show you something. There's this website called PHET, and it has all these simulations, and I want to do some physics simulations. So I go here, and then I'm looking for a whole bunch of simulations here, and I am looking for one to do with sound or waves. So I'm going to look here for work energy power, sound and waves. They'll give me the only ones that are to do with sound. And then I'm going to look here. And I'm going to make this, I'm going to click that.
That's like what we did with the rope, right? When you...
That's exactly like we did with the rope. So what I can do is I can take this, it's got a fixed end now, and I do that. And let's get rid of that fixed end. So let's go to loose end, like water. It's like a string that's loosely attached. That's like water. And then let me put a pulse in. And I want to get rid of damping. Well, actually, I want lots of damping. And I want it to be pretty sharp. I'm going to put it like that. And I want it to be big. And then let's fire this thing. So I'm going to go, let's look, fire. Oh, too much damping. Serves me right. No damping. The problem is going to bounce back and forth, but let's slow it down a bit then. So I'm going to reduce my tension, so I slow it down a bit. So there's my crest going. And then, woo, here's my crest coming back. So a crest comes back as a crest. And now my trough comes back as a trough. Okay, let's stop that. Let's reset. And let's change something. Let's change this end to a fixed end. So now when I do this, my crest comes back as a trough. And my trough will come back as a crest. Let's do that. Let's stop that. Now, let's reset. Okay, so I'm getting two types of reflection. And what happens is, if I go to an oscillator, and I start this off, this thing's going to keep oscillating. I'm going to see a family of waves go off. So and as the wave bounces back, it messes with the wave that's coming forwards. Now, this is kind of complicated, but you see the energy is kind of growing and growing and growing. Here's an interesting thing. I'm going to try and play with it and see if I can get this just right. Let's this might not work so well. Let's stop it. And let's reset. So I might not be able to do this. We'll see how it goes. I'm going to turn this up a bit so that I get things going faster. You're not going to be able to see that so easily. Okay, and then look. If you get it's ever so slightly out. If you get everything just right, I'm not quite there. You can get what's called a standing wave. And the standing wave, just like it doesn't seem to travel anywhere. It just seems to exist. And let's see if I can just get one. I should mathematically work it out, but I'm just too lazy. There we go. Can you see how it gets bigger and it just stays put? I'm still not quite there. So let's restart. So it goes, and now when it bounces back and it adds to crests and takes away from troughs. And it just grows and grows and grows. Because we're getting constructive interference by reflection. But alternatively, what you saw was, I can also mess up. And I don't know if I can find a frequency that will do it. I can also, maybe my tension will help me. I can also get a situation where, no, I'm not showing it. I gotta figure that out. But I can also get to a situation where I cancel myself. So you get interesting effects having on a string.
It really depends on the length of the
That's exactly. It depends upon the length of the oscillator of the wave system and the wavelength of the wave. If the length of the system is like a whole number of wavelengths, happiness, it will bounce back on itself. And if it's not, sadness, basically. So if I go back here and I go, I'm sorry, I need to go to, well, did I? Let's have a look. Oh, I need to go there. I need to go to here. Is that right? No, let's get rid of that. Oh, no, this is what I want. Cancel. If I go to from current slide. So, here I'm showing this schematically. The waves moving to the right, and then it bounces back. And if it bounces back, sadly, out of phase, I will cancel. But if I bounce back in phase, I will add. So you can get these interesting effects. We get standing waves on musical instruments. What happens is that, I mean, if you pluck a guitar string, it doesn't know what frequency to play. All it knows is there's energy going backwards and forwards. So what happens is you try and make every wavelength. And some wavelengths are just right because as it bounces back, you get the right wavelength for the right length of string. And so you get that frequency sustains. And for other waves, you get the wrong wavelength for the right length of string. And they destructively interfere and they cancel out. So you only hear certain frequencies with a guitar string because you decide on the length of the guitar string and the speed of the wave on the guitar string, which is the wavelength on the guitar string. You can do the same on organ pipes. So we hear, when we pluck a guitar string, we hear a note because it's the right length with the right speed of wave and to get constructive interference of those frequencies. I'm going to do just briefly two more things. So that's interesting. We studied that in physics 2, actually. And then another thing we study in physics 2 is, have you ever noticed that when a vehicle's coming towards you, it seems like it's revving up, and when it's going away from you, it's a low tone? That's not... I used to think when I was a kid that car just changed gears. I knew enough about cars to know you change gears, and when you change gears, the engine sounds different. So I used to think when the car went past me, it changed gears. But it seemed like every car changed gears, you know. And then after a while, there's this thing about children where they don't realize that other people are just like them. And so I remember when I was about 6 or 7, my buddy had a birthday party. And at the last minute, I couldn't go to it. And on the Monday morning, I was shocked that the birthday party still took place. It wasn't even that they had took. It wasn't. My feelings weren't hurt about the fact that they had the party without me. It was the fact that I realized, oh, they have lives of their own, independent of me, and I'd never really thought about that before. It was the weirdest thing. This sense of self to some extent. Well, after a while, you realise the car's not changing gear when it goes past me because it didn't change gear when it went past the person in front, or maybe they're changing gears all the time. But you realise there's something going on. What's going on is that it's a very interesting effect. So if I have a speaker, a car, and the car is coming towards me, I'm sorry, I messed up there, so let me go back and put my pen. If the car's coming towards me, then that wave takes a certain amount of time to get to me, and it's here now, and it's here now, and it's here now, and it's here now, and it's here now. So it's traveling at a certain speed towards me. And if I don't move the speaker, then the next one occurs, and that takes its time to get to me, and the next one occurs, and that takes its time to get to me, and the next one occurs, and that takes its time to get to me. So it's like 4 compressions are sent out, and 4 compressions arrive, and they arrive a bit later in time, but it's the same rhythm. If you're like 1, 2, 3, 4, or hum, I'll hear it a bit late, but I'll hear it just the way it is. But if the speaker is closing in on me, then the second wave doesn't have as far to travel, so it arrives a bit earlier. And the third wave doesn't have as far to travel, and the fourth wave doesn't have as far to travel because the distance is getting shorter to me. The distance left is getting shorter. So although the speaker's saying 1, 2, 3, 4, after a delay, I hear 1, 2, 3, 4 because I've shortened the distance. So the last one arrives sooner than expected. And if the speaker's moving away from me, then the last one has a lot further to travel to get to me than the first one had. So it arrives relatively late. So the speaker says 1, 2, 3, 4. And after a delay, I hear 1, 2, 3, 4. A lower frequency. This is called Doppler effect. And it happens with sound. So when a car's coming towards you, it goes, and then when it gets past you, it goes, so you get, as it goes past you, yeah? And light does the same thing. So if I look at, say, green light, and that light source is moving towards me really quickly, it will have a hue which is towards the green-blue end. It's going to go from green a bit more towards the blue. And if that thing is moving away from me, it will go from green towards the red end of the spectrum. How can you tell? Sometimes for species like hydrogen, there's a very specific pattern of colours. And you recognize the pattern by the spacing between the colours. A neon light does the same thing. If you look at a neon light carefully with a spectroscope, you see different patterns of colours. And those different patterns of colours are a fingerprint for neon or hydrogen or helium. And when they look at distant stars, distant galaxies in some cases, they see the very familiar fingerprint for hydrogen. So it is hydrogen. But everything's red shifted. Everything's redder than it should be. And that means that that galaxy or that star is moving away from us. And sometimes with stars in our galaxy, they are blue shifted. And that means that star is moving towards us. Andromeda galaxy is moving towards us. We're going to collide with Andromeda. Most galaxies are moving away because the universe is expanding. And the reason why we know the universe is expanding is because of this redshifting. We can even tell how fast the universe is expanding. And we can wind the clock back, and assuming it's a constant rate, we can say when the universe was born. Now we're assuming a constant rate, you know. But if you think about it, that's kind of amazing. That's like we're taking light and we're recognizing what gas is there, and then we're able to see from the Doppler shift, we assume from the Doppler shift it's moving away from us, and we can even tell how old the universe is. It's the most amazing thing. Now, there's some assumptions there, but until we get some good reason not to believe them to be true, we believe them to be true. You know, that's the whole thing about you have a hypothesis and you check it out, and if it works out, you get a theory. A theory is a good thing. A theory is not a bad thing. A theory is good. And then if that works out a lot, we get a law. So at the moment, the universe is expanding, and we can tell we're 14.7 billion years old as a universe. Let's end there.